So far we've looked at finding the derivatives and integrals of the natural log function. Now let's look at its inverse function, which is e to the x. The first thing that we'll be looking at is derivatives, and then we will be getting into integrals. At the end of this lesson, you'll be able to find the derivative of a natural exponential function. Alrighty, the derivative of a natural exponential function, we're going to let u be a differentiable function of x. If I have y equals e to the u, and actually first of all more specifically if I have y equals e to the x, when I find the slopes of the tangent lines of each point of e to the x, so here's what my e to the x looks like. If I find all the slopes of the tangent lines and then graph the slopes of the tangent lines, I will get the exact same graph. So the derivative of e to the x is e to the x. It is its own derivative. So if I have y equals e to the u, then my derivative will be also e to the u. The only thing I'm going to add to this is it will be du, because if I have something up here other than just x, we do have to take the derivative of it. We have to apply the chain rule before we are done. So pretty straightforward. Alrighty, here we go. Let's see if we can do some that look straightforward. We have f of x is equal to e to the 1 minus x. First of all, we know the derivative of e is its own derivative. The only thing that we need to be concerned about is we're going to pick our u. So our u will just be the exponent. So when I go to take the derivative of this, e to the u is just e to the u, so it'll just be e to the 1 minus x, and then times the derivative of the u. The derivative of 1 minus x is negative 1. Okay, the way that I would clean this up, we generally don't put a negative in the end of our problem, we put it in the beginning, and voila, we've got the derivative. Okay, let's try another one. We've got y equals e to the 5x squared. So we're going to turn this into e to the u. We know that the derivative of e to the u is just e to the u. So the derivative of e to the 5x squared is just e to the 5x squared. And then we have to multiply by the derivative of that exponent. The derivative of 5x squared is 10x. And again, we usually write the 10x first. So the way that I would clean this up would just be 10x e to the 5x squared. And once again, we've got it. Alrighty, next one. Find the slope of the tangent line to y equals e to the 4x at the point 0, 1. We know that the slope of the tangent line is just the derivative, so that's exactly what we'll be doing. We don't actually have to find an equation. We just have to find the slope. So if I look at this, I've got e to the 4x, so I'm going to let my 4x be u. We know the derivative of e to a power is exactly what it is, so e to the 4x is just e to the 4x, and then times the derivative of that u, which would be 4. I'm going to clean it up first, so I'll get 4 e to the 4x, and then we would like to find the slope of the tangent at 0, 1. So my x in this case would be 0, so 4 e to the 4 times 0. 4 times 0 is 0. E to the 0 is 1. 4 times 1 is 4. So the derivative at 0 is equal to 4. Alrighty, example 4. Use implicit differentiation to find the derivative. So remember, implicit differentiation, wherever we have a y, we need to include dy dx. Alright, first point, we've got x times e to the 3x. So first thing that I do need to do, because there actually are two functions being multiplied together, I actually have to use the product rule on this one. So f prime will equal 1. G prime, notice we've got an e to the u problem going on. The derivative of e to the 3x is just e to the 3x, and then multiplied by the derivative of that u. The derivative of e to the 3x is 3, so this will be 3 e to the 3x. Now I'm ready to take the derivative of that. So we're going to have f prime times g, so 1 times e to the 3x, plus f times g prime, x times 3 e to the 3x, and then minus the derivative of y would just be 1 dy dx, and then equals the derivative of e to the x is just e to the x. If I wanted to replace this with u, notice the derivative of x is just 1, so I don't really need to write times 1. Okay, cleaning this up just a little bit before we simplify. This is going to be e to the 3x plus 3x e to the 3x minus dy dx is equal to e to the x. Please remember that if I'm solving for dy dx, I want all the dy dx's on one side and everything else on the other. I'm actually going to make this a little easier. I'm going to move this to the right side and the other one to the left. So I'm going to have e to the 3x plus 3x e to the 3x minus e to the x is equal to dy dx. So from here, I'm pretty much done. I do all notice that they have an e to the x, so I'm actually going to go one more step. My dy dx will equal, I'm going to factor out an e to the x. And if I factor out an e to the x, when I factor it out of 3x, I'm going to have e to the 2x. Please remember, when I do that, if I add those exponents, x plus 2x, I get 3x. So that's why it's just 2x. And then plus 3x e to the 2x once again, and then minus if e to the x divided by e to the x is just 1. So that would be my derivative. Alrighty, this time we'd like to find all the x-coordinates of all relative extrema of the function f of x is equal to x e to the negative x. So I know with relative extrema, we're looking for mins and maxes, and we're going to make use of an f prime chart to get there. Alright, so I need to find f prime. I do notice that I have a product going on again, so we're going to label f and g. F prime, the derivative of x is 1. And then g prime, I've got an e to a power, we'll let that be u. The derivative of e to the negative x is just e to the negative x times the derivative of negative x, which is negative 1. So cleaning that up, that would be negative e to the negative x. Alright, so finding my derivative, I will get f prime times g, 1 times e to the negative x, plus f times g prime, x times negative e to the negative x. Okay, I'm going to clean this up just a little bit. We're going to get e to the negative x minus x e to the negative x. So that will be my derivative, and I'm going to set that derivative equal to 0. So e to the negative x minus x e to the negative x equals 0. So I can find a critical number. If you're not familiar with what to do on here, I notice they both have an e to the negative x, so I'm going to factor out an e to the negative x. So I will end up getting 1 minus x equals 0. And now pretty much what we're going to be looking at is what would make each part equal 0. Okay, if I have an e to the negative x, that would be the same thing as 1 over e to the positive x. And we know that from studying the exponential function, that an exponential function, it looks something like that. And you'll notice that this will actually never equal 0. So this part will never equal 0, so we don't have to worry about it being a critical number. On this part, that would equal 0 if x equals 1. So we're going to go ahead and do our f prime chart, and we're going to put 1 on it. And I need to go back to the derivative, and I actually think I'll go into the factored form. If I plugged 0 into here, no matter what, just to save myself some grief if I don't have a calculator, I know what e to the x looks like, and I know that this is always going to be a positive value. So this is always going to be positive, so I don't really even need to plug stuff into it. So if I plugged 0 into this part of my formula, I would get a positive. If I plugged 4 in, I'm going to get a negative answer. So based on that, if I'm looking for relative extrema, I can tell that at x equals 1, there's going to be a relative max, and that will be because f prime changes from positive to negative. And I should notice if I were to actually graph this function, I should see there be like a hump or something like that at x equals 1 because there is a relative max there. So hopefully now you can find the derivative of an exponential function involving a base of e.